teach the pattern transfer lithography. So far we have most of the process we learned is actually without pattern. For example, the epitaxy, the oxidation, the implantation. So you just do it through the blanket wafer. You can also do it, of course, with the pattern wafer. But today we are going to teach how you can form those various patterns and why you can have patterns formed. Okay, and this step we call it lithography. Okay, here is the outline of this whole chapter, but now I don't require you to go through this one. Later, after we finish, and you will know each of these items. And this one also the learning outcomes. So after you finish of this chapter, you go back and check the learning outcomes to see whether every point you understand. Well, of course, in my class, I will give you those most important ones. Okay? So those ones are 80-90% of your final exam. Okay, so before I do this lithography, so we talk about dimensions. Because you form the different patterns, you basically have different dimensions of these patterns. So I will introduce of this ITRS map. So ITRS is International Technology Roadmap for Semiconductors. So this is very important. This is a very important one when you talk about semiconductor transistors. ITRS. Okay. International Technology Roadmap for semiconductors. Okay, so this is like an organization where some of these famous people from the academia and also from industry, so they will make a prediction of what our technology will go for the next few years. So this is also like the guideline for researchers and industry people in our field to target. So what are the dimensions, what are the device performance you have to do in the following years, okay, a few years. For example, if we look at this, you see, here I talk about 16 nanometer technology node, okay? This 8 nanometer, 7 nanometer technology node, 5, 3, and later at 2027 you have 3 nanometer, and then going forward 2030 you have 2 nanometer, okay? Or if you look at this name, okay, the name, or if you look at the dimension, the gate length, okay, gate length, you can see that it's not actually 2 nanometer, right? It's not 2. So these are just for advertisement, just for those companies to attract the customer's attention, okay? So those are not the actual physical gate length, okay, of the transistors. These are actually one, and people are trying to target.
What is LP and HP?
HP is high performance. HP high performance. LP is low power. So for transistors, you will have different types of transistors. In the circuits, IC circuits, okay, some of the portion you need them to have very high performance, okay, but some of them you don't need them to have very high performance. For example, those are for control, then you don't need. For computing, you want very high performance, right? For those control one, you don't want to high performance, but of course you want them. All of them actually want them to have very low leakage current, okay. So, but some of them, but when you have low leakage current, normally you will have low performance also. So people do this by tuning the threshold voltage, and of course some other techniques. But here you see that HP is high performance, LP is the low power. And okay, so here we all talk about the dimensions, right? We have the very small dimensions, a few tenths of nanometer. You see? So how can you achieve these small dimensions? How can you achieve different type dimensions? Actually, in semiconductors, you have dimensions from a few nanometer all the way to a few tens of micrometer. Okay, how can you all have all those different dimensions of patterns? Okay, this is to introduce all this one is by a technique we call lithography. Okay, so this will introduce to the topic we're going to talk today. Okay, traditionally lithography actually accounts for a very significant part of the total wafer manufacturing cost. Okay, like 5 years back. Okay, this one accounts for just for the lithography. Okay, forming the patterns, different masks, you will have to cost about 1/3 of your total cost. Okay, but nowadays it is even be more than I think half of the total cost, because when you have smaller and smaller dimensions, how can you achieve those dimensions becomes more and more expensive. It's not easy anymore. Okay, now people are using EUV, which one tool is more than one airplane, 777 Boeing 777 airplane. So it's very expensive now, and the power to just support this one is very expensive. Like Taiwan recently got some problem of the electricity, and it's very actually people see from the airplane. Okay, when they see those the foundries, okay, from the airplane, they found that there are very obvious section of this foundry, and those ones actually are built just for support this EUV tool. So it's becoming more and more expensive for this lithography. Okay, and so when you want to have different types, different dimensions of this pattern, actually you have to use different method. Okay, such as optical lithography. Okay, use the light. Use light to generate the light source. You also have X-ray, because X-ray has much shorter wavelength, so you can achieve smaller dimension as compared with optical. And now we can even have electron beam, okay, which can achieve even smaller one. So different dimensions, you can use different types of lithography tool. EUV here, I think it stands for extreme ultraviolet. Okay, this one just later you will know more and more. Here I just give you introduction. But now I want to give a very brief introduction of what is the main process for this lithography. Okay, now here is important one. Okay, here is important this slide. Now let's see the main steps when you do the lithography. Okay. Okay, now this is the substrate. Let's say silicon substrate. Okay. Now we put some film. Let's say we have silicon oxide layer. Okay. Silicon oxide is amorphous or crystalline. Okay, good. Okay. You have, let's say, silicon oxide. This is the wafer. Okay. Now we want to form pattern on this wafer, especially on this silicon oxide layer. Okay, this is blank silicon oxide, right? What we do is that first we spin coat, okay, or photoresist. This photoresist is liquid. It's an organic chemical. Okay, you don't need to remember what exactly it is because it's very complicated, like CH++, many very long. You just know that it's an organic chemical, okay, and it's liquid. What we do is that, okay, if this is a wafer, this is a substrate, so it will rotate. Okay, you have a machine. You put this guy on a machine, okay, like this one. Now you will like rotate of this one. Okay, this machine can have a rotation of this wafer at a speed of thousands, okay, per second. Thousands rotation per second with this speed. And now you put this photoresist. Because photoresist is liquid, right? You put them on this surface, and because of this rotation of this wafer, so this liquid, this photoresist will be spin coated onto the surface. Okay, the thickness of this guy varies based on the types of PR. So when I say photoresist, I also say PR. From now on, I say PR. It's not permanent resistance. It's photoresist. Now I will call it PR. Okay. So the PR, the thickness of PR depending on the PR type you use. It also depending on the speed of this rotation. Okay. Normally the thickness of this PR after you finish of this spin coating is a few tens of nanometer to a few micrometer, the thickness. Okay? Okay, after you spin coat it, you put the liquid on top and because you are rotating very fast, it will be uniformly coated across the whole wafer. And the thickness of that PR is a few tens of nanometer to a few micrometer, depending on the PR you use, depending on the rotation speed you use. Okay? And okay, this is the second step. Okay? After we finish the second step, so we will then the next step. So how can we have the form the various patterns? Like you want to have squares, you want to have the circles, and you have different dimensions of lines. How can you have these patterns? So we will have a mask. This one is called mask. Okay? There is a mask. You put the mask on top of this PR. Okay? And this mask can be direct contact with this guy. Okay? It can be approximately away from this one, like a few tens of nanometer, a few tens of micrometer. And it can be further away. Okay? But those patterns you want to form on this PR actually are on this mask. Okay? This mask can be used many times. It always can be reused. Okay? It's just mask. And on this mask, you have the patterns which you want to form on this PR. Okay? And how can you have different patterns? And in this region, like the dark region, okay, the light cannot go through. So light is blocked. Okay? And in this region, in this white region, the light can go through. Okay? So what is the difference when you have light go through and light cannot go through? And this is the magic of the PR. Okay, so for PR, once the PR sees the light, okay, the PR which sees the light will change the property. For example, in this region, the PR will see the light. Okay, in this region, the chemical property of this PR will be changed. Of course, those one without seeing the light will not change their property. Okay, so now because this region you already changed the property, this region you don't change the property, and now you put this guy into a chemical, okay, which we call developer. Where is my?
Under the node.
Oh, this one. Okay, you put this one into a solution. Okay, and that solution is called developer. You have to remember this guy. Developer. Okay. You put this exposed sample, okay, into a solution, and this solution is called a developer, and the process is called developing. Okay, developing. Okay, once you put this guy into this solution, okay, let's see. In this case, those one has exposed with light will be removed, will be dissolved into the developer. Like this one, you see here has solar light. When you put into the solution, this one will be gone. This one will also be gone. Okay? And those without seeing the light will stay there. Okay? And now you see, you have the patterns here. Right? What is your question? Just say.
Oh, I want to ask. Actually, you use mask. Why we still use the photoresist?
Why we use it? Because photoresist has the property where it will change your property after exposure of the light. Right?
For H.
Yeah. Right? You must choose a property where you can form the patterns. You can have different patterns, right? Okay, let's say now you don't have a PR. Let's say we put this one. We just put this one without PR. Okay? Then after expose your silicon oxide. The silicon oxide without light, with and without light, there is no change. And then you put this into a solution. What can you change? You still have the same material, right? The reason for this one is to have the sensitivity of light, so that it can change the chemical property after the light exposure. Correct? You understand, right?
Which one is developer is what?
Developer is so after we do the exposure, we put this into a solution. It's also a liquid, a solution, and those solution can remove these areas with light or without light. Okay. That one is called developer. Just like let's say you put this one into a water. If you put it in a water, and if water can remove something of here, okay, the water is called developer. Basically, is that solution. You are confused. Why is confused? Okay, this one is important. That's why I spend more time. If you have any questions, let me know, because later this is the basics for later. Which one you are confused?
From the third step.
This one? Okay,
Yeah.
this one, which one you confused?
Because that's why I'm not yet.
Oh, you're not here. Okay. So, where is your friend?
On the way.
He's on the way. Okay.
The printing the notes.
Okay. This one spin coating, you know, right? This one is spin coating. After this one, okay, you put this one under object which is called mask. Okay. We want to form the various patterns on this guy, right? So the pattern is actually also printed. It's actually in this mask, and this mask can be used many times. Okay, the pattern is there. So on this mask, there are regions where you have the portion where the light cannot go through. Okay, and you have the portion where the light can go through, and those portions actually depending on the pattern you want, right?
Okay.
You want different patterns. You want squares. You want lines. Then you just put based on your requirements. You some places you have the place where you don't want the light to go. Some places you want the light to go. Okay. Then after you do exposure means that you have the light exposure. Okay. In these areas, you see these areas will see the light, right? Because light can go through, right? These areas, the light will not go through, right? Because it's blocked by this guy. So the magic thing of the PR means photoresist, is that once you see the light, you will change the property of the PR. Okay? Once you change the property of the PR, and then you put them in your solution, okay? Okay? Because this PR, you see these two guys, the property now is different from this one, right? And then when you put them into a solution, some of them, for those with the light, will be dissolved in the solution, and with those without the light, okay, will be stay there.
Okay.
And now you see you form the pattern. Understand now? Okay. So this is called development. It's developing. It's just the means. It's the noun of the developing. Okay. And this solution is called developer. Okay. And this step is called exposure. It's also called light exposure. Means that the substrate is exposed to the light. Okay? Because when you do this one, you put a sample, you just put a sample there, and you switch, you press a button, and then the light source will on. After a few seconds, and it will switch off. Okay, that's why it's called light exposure. Okay, so actually the lithography step includes only major one is 1, 2, 3. After this one, this two is not lithography. It's not. This is just use etching. So this one is called etching. Later I will talk. In the next chapter we'll talk about etching. Etching basically means that you want to remove the material. You remove the material. For example, here we want to remove the silicon oxide. You just use etching, your physical and chemical bombardment, and you can remove this area. And this area cannot be removed because this guy is blocked by the photoresist. Of course, some of this etching, depending on the chemical you use, okay, you can etch of this PR. Okay, that's why a very, very important thing during the etching is that you must make, because this one is also the mask, right? Okay, this mask is different from this mask. Okay, this mask is the one way for the lithography to exposure, but this one is during the etching. But we also call it mask. Mask means that we protect the area where we don't want them to be etched. Okay, so you see, you during the etching you must make sure that this one PR is good enough, strong enough to protect this one not to be etched. But this area you want them to etch, then you just etch them. Sometimes if you do not do well, okay. Sometimes if you do not do well, of this lithography, you maybe end up with the situation. You maybe end up with a situation. Let's say this is silicon substrate, okay, and then we have a silicon oxide. Silicon oxide, okay. Now you have the PR. For good PR, like we